Quadrant sensor, Ranger, neutron and gamma detector and identifier. I've used it with two samples. The first one is the welding rod, and it is here, as you see. I put a plastic around it to concentrate the emission, but it was identified as americium. You're going to see here 241. The second sample would be americium that is labeled from the smoke detector 241, and I'm putting it right now on a probe. It's a household smoke detector. Number 3, acquire ID. On the right hand corner there is identification of americium 241. Dead time 0, real time 27 counts. The graph shows the range that is sufficient for the measurement. There is 0 neutron counts for this sample. 0 exit 1 auto calibrate to identify. Pressing 2. That's it. That's how much time it took to identify the sample from the smoke detector used commercially in our houses. Advanced. Go to search. Again repeating same. But no identification at search. And now it's giving me the information. The comparison between the old and the new one for the two recent measurements to make sure that it came with the same results. As you see, go to 0. Go to 6 files. Go to 6 files. Go to 1, lessons. User. What's interesting in here is that it gives me summary for that particular event based on the frequency response. You can compare that towards non-standard values. Americium 248, it should be industrial, so that would be number 2. We're looking for americium. There you go. I'll now try to compare the results from part 1 to 3 of Revolution Has Begun, Free Energy Exposed, and compare it to data of this test with additional equipment. First, the introduction. Alpha could be stopped by paper and human skin. Beta could be stopped by thin sheet of aluminum. Gamma could be stopped by lead. Some of the original text from the time of Hendershot, 1926, 1933. But we're investigating Coleman from 1956 patent. For those who are interested to read it. Phosphide and phosphide properties used in a compound. I'll explain here. This is similar Russian device, but it's based on radioactive material that is placed in the vertical glass tube, as I'm using 100% non-radioactive substance. There you go. 27,000, and the dose rate is 0, guys. The upper scale is for gamma radiation and is pretty low. We may assume that we're dealing with alpha particle. The question is why we have a neutron radiation. Neutron rate. Okay, we have had the dose for the moment 0.01. I'm going further, I'm going further. The reason I couldn't make it is because I was in wrong frequency. I've changed the frequency to 440 right now, 440 megahertz. Okay, let's go further, see how far we could go. And the power is 12 watts. I'm releasing right now, pressing, releasing. Still, a short while after releasing it goes out. So 18,000, 24,000, 36,000. The frequency is important. You know what is the frequency. And it's only two layers. 39,000, 40,000, 42,000, 43,000. I'm pulsing it right now. 59,000. And the dose rate that is harmful is 0, guys. Ha ha. 25,000. 36,000. 31,000. 53,000. Oh boy, 129,000. And the dose rate is only 0.3. Ha ha! 119,000. I love it. $30,000. $54,000. So who's gonna tell me that the activation of the compound doesn't happen using the radio wave? Huh? Who's gonna be the one? 35,000, 40,000, 42,000, 41,000, 35,000, 49,000, 80,000, 159,000, 269,000, and the dose rate is 0.07. Still not harmful. 158,000. Okay, there is your proof, guys.
Oh boy, look at that. Look at that. I pinned the needle. Pinned it and I had to change it. Ooh, look at that. Okay, I've changed the range and see what's happened here. It's growing. Am I gonna pin this time? Oops! I pin it second time. We're changing again. Okay. Oh boy. Now I'm a little bit worried because I have a range of 50. Range of 50. Uh-oh. Range of 50, okay. Going further. No kidding. This is not nice. think I found the secret. For me and the neutron count, because we have a huge one, neutron count, I have to just push and release. I broke already 2 tubes. I made the identification of it. I don't know if it's gonna be readable. Okay, maybe like that. Too much reflection. Okay, low 1114 and a high 12,034, 1234, peak 1235 kiloelectrovolts.
From Wikipedia, nucleate cobalt-60, Father uses cobalt-60, synthetic radioactive isotope of cobalt, half-life 5.27 years, produced artificially by neutron activation. Well, we've got plenty of it, but we don't have a cobalt-60. Of the isotope 59, and then cobalt decays by beta decay, possibly. We might have beta or alpha or both. To stable isotope of nickel 60. Well, nickel is the one that Andrea Rossi was playing with, so that might be part of his puzzle. As we have a heat associated with that, he's using only the heat exchange. The activated nickel nucleus emits gamma. Well, we don't have a nickel, we don't have gamma. So we don't have 1.17 and we don't have 1.23 mega electrovolts. And for those who wants to read that, is how the activation happened. Although not necessarily we have exactly the same process. We don't know yet what compound is produced during the transmutation eventually. The nuclear magnetic resonance associated with it. We don't want to give any data that will be misleading. That has to be checked. But we did check it with 2 different instruments, and it looks like we don't have gamma. At least I didn't notice gamma. I open up the window from Radiac, the old metal one, and that allow beta and alpha particles to come in. So now the question is, which one do we have, or both? Neutron activation is a process in which neutron radiation induces radioactivity in materials, and occurs when atomic nuclei capture free neutrons, becoming heavier and enter excited states. It's about the activation. The excited nucleus often decay immediately by emitting particles such as neutron, protons, or alpha particles. Well, which one do we have? Or both. The neutron capture, even after any intermediate decay, often results in formation of unstable activated product. Well, do we have it? I believe we do. Such radioactive nuclei can exhibit half-lives ranging from a small fraction of seconds to many years. An example of kind of nuclear reaction occurs in the production of cobalt-60. We don't know what we produce yet. We find something about it. The cobalt-60 then decays by emission of beta particles plus gamma rays into nickel-60. Well, we don't have it. We don't have nickel-60. Andrea Rossi does it. This reaction has a half-life of about 527 years. Okay. In other cases, depending on the kinetic energy of neutron. Okay, so there we go. The kinetic energy of the neutron is not a fixed number. It is bigger or smaller. The capture of the neutron can cause nuclear fission. The splitting of atomic nucleus into small nuclei requires input energy that comes from kinetic energy of neutron. In other words, the capture of neutron from beryllium-9 causes it to split into two energetic helium-4 nuclear alpha particles. Plenty of this thing could be read by the description of neutron activation. Time to wrap it up. We see what we see, we don't know yet what we have. We have some results, we have confirmation with two different devices. We have preliminary findings, and we're going to proceed. We didn't extract the electrical energy out of it as Coleman did, because the compound that I use is an oxide. That means the chemical part of it that is supposed to react is reacting. It shows huge neutron emission. No gamma. At least I don't know why it didn't show gamma, but it didn't show gamma. That's good. So beta or alpha only. Well, alpha by itself is 5,000, no, I'm sorry, 5 mega electrovolts, comparing to beta, which is 100 kilo electrovolts. You see the difference? Huge one. And alpha could be stopped by paper or a skin, human skin. You gotta read more about it. The legal note would be never touch it, never do it, never. Don't do it. And the note that is not associated with that legal statement is ha ha ha. Thank you very much, guys. Have a good one. As a legal note, I forgot to add additional formula for bloodsuckers to leave me alone. We are not responsible for opinion expressed. In other words, I don't know what I'm talking about. I'm not gonna show you my fingers. Some of you bloodsuckers. With these words, I wish the best to this great nation, United States of America, which I'm proud of being one of them. Have a good night.